Hello everyone, welcome to another episode of Revernos. In today's video, we'll be continuing our machine learning series and we'll be going over linear regression. So let's dive right in. Let's go over a quick agenda before we dive into the content. We'll begin this video by explaining what is a linear regression, and then we'll tell you how does a linear regression work. We'll tell you the assumptions that have to be true before you can use a linear regression. We'll talk about some of the features of a linear regression. We'll talk about does linear really mean linear, and we'll talk about some ways you can even do a nonlinear regression. We'll talk about how you can evaluate a linear regression. I'll give you the code you can use to implement a linear regression in Python using sklearn. We'll talk about some ways you can improve your linear regression model, as well as when should you use a linear regression. So let's start by talking about what is a linear regression. Linear regression is a supervised machine learning model. In reality, there are multiple different linear models for regression in machine learning, but in this video, when we say linear regression, we will be referring to the ordinary least squares, or OLS linear regression, which is the most common form of machine learning. And when we get to some of the features of this OLS regression, you'll understand why this is the one that's most used. So how does a linear regression work? In algebra, you may have learned that a line takes the form y equals mx plus b. You may have learned it with different letters, but essentially m is the slope, x is the x value on the Cartesian plane, b is the intercept, and y is the y value on the same Cartesian plane. Linear regression essentially works by fitting a line of best fit through your data points that minimizes the sum of squared errors. The error is the difference between the actual and the predicted value, so this regression minimizes the total sum of those squared errors. What this really means is that this algorithm finds the m, which is the slope, and the b, which is the intercept, that gives you the best possible predictions, once again by minimizing the sum of squared errors. So if you look at this first graph we have, let's say we're looking at age and its effect on income. So in this example, age would be our independent variable on the x-axis, and income would be our dependent variable on the y-axis. And you can see the trend here. So you can see in general, when age increases, income also increases. This is just a really basic example, and we'll be actually implementing this in code using some mock data later on in the video. But you can also see there are some outliers, and we'll talk more about outliers later in the video also. But in general, you can see that age increases, income also follows that same trend. So there's a positive linear relationship in our fictitious data here. And what regression will do is fit a line of best fit through our data points. So let's say that line of best fit looks something like this. Remember, when a linear regression learns, it's learning the values for the slope and intercept that give you this line of best fit. So this red line will then be used to make predictions in the future on our testing data. So let's say in this graph, the black circles are data points from our training data, and we have a new red circle that will represent a data point from our testing data. And we know the age of this person, and so we're trying to predict that person's income. So we know their age. If you go to that point and you go down to the point on their x-axis, that would be the corresponding age. And once we have our line of best fit, we will go to where they are on the x-axis, plug that into our red line, which is our linear regression model, and then it will give us a corresponding prediction for, based on that person's age, what does the model predict their income will be. And so here we can see that this blue triangle represents our predicted value for this person's income. Now we know that this red dot, because this is a supervised machine learning algorithm, we actually know what this person's income is. And so there's a difference between what their income actually is and what we predicted their income would be. And we'll represent that with the yellow line. And this yellow line will be called the residual. The residual is the difference between the actual and predicted value. Before you can implement a linear regression properly, there are 7 assumptions, and 6 of those assumptions have to be met. And then the 7th one is a nice to have that we'll talk about later. The first one is that your data can actually be modeled with a linear regression, which seems obvious, but if your data can't be modeled in a linear fashion, and we'll talk more about whether or not linear actually means linear. But if your data can't be modeled in a linear fashion, then this will not be the algorithm for you to use. The second assumption is that your error terms have an average value of 0. If this assumption is not met, then the error terms are predictable, and that is important information that's missing from your model. If the error term is consistently negative or positive, then your model is consistently predicting incorrect values, and that means your model has a bias problem. The error terms in your model, on average, should be 0. The third assumption is that the independent variables are uncorrelated with the error term. If this rule is not met, then the error term can be predicted, which violates the assumption that the error term is random. If the error term is not random, it can be predicted, and once again, that means there's additional information that needs to be included in your model. The fourth assumption is that error terms are uncorrelated. If they are not uncorrelated, an error term can be used to predict a subsequent error term. Then the error terms are correlated. This issue is called autocorrelation or serial correlation. You may be able to remedy this issue by including past observations of independent variables inside of your model. The fifth assumption is called homoscedasticity. This assumption means that the variance of the errors is constant across all observations. If the variance changes, that is called heteroscedasticity. You can see if you have constant error terms or not by graphing the errors. So let's look at these two examples here. On the top one, imagine these black dots are error terms, and this black line represents a value of 0. Top example, we can see that as age increases, the residuals have the same average across all levels of age. But on the bottom example, we can see that the residuals are not constantly hovering around 0. On the bottom example, as age increases, so does the average value of our residuals, which means we have heteroscedasticity. The sixth assumption of an ordinary least squares linear regression is that no independent variable is the perfect linear combination of another independent variable. This is saying that none of your independent variables can have a perfect linear relationship with any other independent variable. Perfect linear correlation means that the Pearson coefficient is -1 or +1. Even if two variables are not perfectly correlated, but they are strongly correlated, that can lower the accuracy of your model. This issue is called multicollinearity. If you have two perfectly correlated variables, you should exclude one from your model. The seventh assumption, which is more optional than mandatory, is that your residuals should be normally distributed. If this is true, then you can do more accurate hypothesis testing and have more reliable confidence interval. But if it's not true, then it won't cause major problems for your model. Now let's move on and talk about some of the features of an OLS linear regression. There is a theorem in statistics called the Gauss-Markov theorem. This theorem states that when the first 6 assumptions we just talked about are met, the OLS linear regression is the best linear unbiased estimator, or BLUE for short. This essentially means that the OLS method will give you the least variance and bias when compared to other linear models when the first 6 assumptions are met. We've been using the word linear a lot in this video, but does linear really mean linear? We have been calling the OLS regression a linear regression because it fits a linear line. However, it can be used to fit a nonlinear curve. This can be achieved by performing some algebra on one or more of your independent variables, such as taking the natural log of an independent variable, and then using that altered variable in your model. The model will still use the OLS method to calculate the coefficients and intercepts, but it would fit a nonlinear curve instead of a straight line. Now I'll actually show you how you can implement a linear regression in Python using sklearn. So we'll start with some import statements. You see we import numpy is np, pandas is pd, and then from sklearn linear model we'll import linear regression, which is what we'll be using to run our regression. And then from sklearn model selection we'll be importing train test split, because you should always do a train test split on your data when you're doing any sort of machine learning. So the first thing I'll do is import my data. I'll be using some mock data that I generated for this video, but any data set you have with numerical features will work fine. Of course, each data set will require different amounts of data pre-processing, which we're not covering in this video, but a regression works on a ton of different data sets and can give you good results. So now that we have our data, we need to create our training data and our testing data, and we'll do that by running the train test split function. So we'll do xtrain, xtest, ytrain, and ytest, and we'll call our train test split function. Remember, we're using age as our independent variable, and we're using income as our dependent variable. So we'll run that. And now let's look at our training data. So we can type in xtrain and run that. You can see on the right here, we have the ages. And these are just the shuffled indices, so we don't have to worry about that. So let's go down to a clean cell. And you can see that our data here is one-dimensional, but the input has to be two-dimensional, so we'll reshape it using a NumPy function, np.array. And it'll take an xtrain, and we will reshape that to -1 and 1. Then when we run that, we'll see it gives us our output, or our training data is a two-dimensional array, which is what we need to input into our model. So actually we can highlight this and copy that. And now we'll actually build our model. So we'll just call this regression model equals linear regression with parentheses dot fit. And then we'll just paste what we just copied into there, which will be our two-dimensional training data. And then we will train it with ytrain also. And it's fine if that's one-dimensional. So we'll run that. And then we'll take our model and we'll see what our squared value is like using the score method. And once again, we will pass in that same thing, but we'll use xtest instead of xtrain, and then ytest. And let's see how our model performs on the testing data. You can see we're getting an R squared value of 0.876, so about 88%, which is actually very good. But remember, we're just using fictitious mock data here, and this is just a lightweight example showing you how you can actually implement this in Python. So don't pay much attention to what this score actually is. Now that I've shown you how you can implement a linear regression in Python, let's talk about some ways we can improve our model. You can experiment with different variables and also experiment with including variables in different combinations and then choose the model that works best. You can One way you can improve your regression is to experiment with different variables and different combinations of variables and then choose the model that performs the best. You can also perform exploratory data analysis and include the variables that you think make sense. You may also want to eliminate outliers to prevent them from weakening your predictive power. You may also consider using adjusted R squared in conjunction with the traditional R squared. You may be able to increase your R squared by including a lot of extraneous variables in your model, but adjusted R squared will penalize adding extraneous variables, so you should consider using that metric in addition to the regular R squared. The fourth way you might want to consider improving your model is to transform your data. For example, you can consider taking the log of some of your variables. You could consider normalizing or standardizing some of your variables, and you can just experiment with different data transformation and see which ones improve your models. Now we'll talk about some of the pros and cons of this method. Some of the pros are it's simple, easy to understand and explain to others. There are no hyperparameters you have to tune, and it can perform well with multiple variables. Some of the cons, it can be thrown off by outliers, but you can address this by removing outliers. Another con is this model has to follow the assumptions we talked about earlier. For example, no multicollinearity or heteroscedasticity. And other models may give you better performance, so you might also want to experiment with some other models to see which one gives you the highest accuracy. So when would you use a linear regression? If your dependent variable is numeric, so this will be a regression problem, not a classification problem. If you plan to use this model for inference, even though it can be used for predictions, this model is often used for inference. For example, if you just want to see the effect that an independent variable has on a dependent variable, and you may or may not be worried about predictive power. Or if you need a model that's simple and easy to explain or quick to implement, then you might want to go with the regression. If you like this video, be sure to like, comment, and subscribe. When you subscribe, click the notification bell so you don't miss an upload, and also comment saying you subscribe, and I'll try to like or heart all the comments. We have a machine learning series on our page where you can check out other videos in our machine learning series, and we also have a lot of videos coming in the future about programming in Python, machine learning, artificial intelligence, cloud computing and Amazon Web Services, and physical computing using Raspberry Pis. So we have a lot of great tech content coming in the future, so make sure you subscribe so you don't miss any of it. Thanks for watching, and I'll see you in the next video.